Welcome. Thank you for joining us as we explore our paper MFT, long-term tracking of every pixel. Our paper deals with visual tracking. Standard visual object trackers track an object from the first video frame throughout the video using a bounding box or a segmentation mask representation. Applications like structure for motion or video editing shown below benefit from long-term dense correspondences. Optical flow methods output dense correspondences, however, only between pairs of frames. Our method, called MFT or Multi-Flow Long-Term Tracker, extends optical flow to dense long-term trajectories over the whole video sequence. For each point in the first frame, MFT outputs the points, position, and visibility in every other frame of the input video. A baseline approach is to simply chain the optical flow fields computed on consecutive frames. The diagram at the bottom left shows a toy example of the chaining. The x-axis represents the frame numbers and the y-axis the position of a tracked point. For simplicity, the diagram shows just one-dimensional position. As shown on the video, such approach cannot recover from temporary occlusions. Moreover, even on non-occluded areas, small errors in the optical flow accumulate over time, leading to a large drift. Another approach is to estimate the optical flow directly between the template frame and the current frame, drawn as the bold arrow in the diagram. This way, the optical flow errors do not accumulate, and since the estimation is done independently for each target frame, the direct matching approach can recover after failure. However, the direct matching is a harder task due to change of viewpoint, change of illumination, and large motions accumulated over time. The video shows a failure caused by a significant camera rotation and recovery on later frames. Apart from the simple chain of optical flows and the direct matching, there are other possibilities. For example, the target point could be tracked by a simple chain for 2 frames, followed by an optical flow from frame 2 directly to frame 5, and finally by another simple chain to the current frame number 7. This chain could be a good choice, for example, when there's a short-term occlusion on frames 3 and 4, or other conditions that would cause optical flow and accuracy on those frames. There are other options, like these 2 examples. The number of possible chains grows fast with the increasing number of frames in the video. Note that the best tracking result could be achieved using a different chaining scheme for each query point. Now, we will describe our MFT method, which significantly reduces the number of considered chains and selects the most reliable one. Let's go over MFT, tracking example frame by frame. The MFT selects the simple optical flow to the first frame because there are no other chain candidates. In the second frame, there are 2 flow chain options. The first one is matching directly between the template and the current frame. The second one is computing the optical flow between frame number 1 and the current frame and chaining it with the result on the previous frame. This results in 2 correspondence candidates. MFT selects the most reliable candidate according to a strategy that we will describe in a moment. Any other candidates are discarded. The selected candidate is marked by the red dot in the diagram. In the third frame, MFT considers 3 chaining options. The result on the previous frame chained with the optical flow between frames 2 and 3 at the top. The result on frame number 1 is chained with the optical flow computed directly between frame 1 and the current frame in the middle, and the direct matching at the bottom. Again, the MFT selects only one of these. This is repeated on each frame of the video. MFT only uses flows spanning 1, 2, 4, and so on frames, and the direct matching flow, denoted by delta equals infinity in the diagram. This significantly reduces the computational cost, making the MFT fast. The whole procedure is done independently for each tracked point. Now, we will describe how to select the most reliable candidate. We estimate uncertainty of each optical flow vector and select the candidate chain with the lowest overall uncertainty. To compute the overall uncertainty, we sum the uncertainties of all the flow vectors in the chain. Nowadays, typical optical flow methods extract features from both input images and construct a correlation cost volume, which is then used as an input to an optical flow regression head. In MFT, we extend this with a small uncertainty estimation CNN head, which outputs an uncertainty score for each optical flow vector. We train the uncertainty head on optical flow datasets using a pretty standard uncertainty loss. During training, the network can balance a high error of the optical flow by predicting a high uncertainty score sigma. To avoid zeroing out the loss by predicting high sigma everywhere, the loss function contains a regularization term. Standard optical flow methods are trained to work even in occluded regions, which is possible thanks to the surrounding context. In the top right example, the estimated optical flow is correct and has low uncertainty. But MFT cannot continue tracking this point as it would drift from the target point on the head to the occluding bamboo. Because of this, we extend the optical flow network with another small CNN. That is trained with binary cross entropy to estimate the occlusion map. In MFT, the candidate flow chains that contain any occluded flow vector are removed from the candidate pool. Since there is no benchmark for dense long-term tracking, we evaluated MFT on a standard sparse point tracking benchmark, TAP-Vid, which has ground truth tracks for around 20 points in each video. MFT performs competitively to concurrent work which are specialized to sparse point tracking while being orders of magnitude faster when applied for dense tracking. The slowest part of MFT is the computation of the optical flow. For applications like video editing, the optical flows can be pre-computed, which results in a tracking speed of over 100 frames per second, enabling interactive use. Here's an example of video editing using MFT. We start with the original video. First, we edit the initial frame of the video. Then we propagate these edits throughout the entire video using the estimated position outputs from MFT. Here's another example showcasing MFT's capability in handling non-rigid motions. It can handle these motions without restrictions on any particular target particle. In this instance, MFT successfully recovers tracking even after a significant occlusion. Finally, in our last example, we demonstrate how we change the video's style using just a single example frame of a new style. We then applied this stylized frame throughout the entire video using MFT. The raw results and the code, including a simple demo used to generate these videos, are available online. Thanks for your attention.